So I want to do the canonical view transform, and then I'll be finished with the chain of transformations, and then we'll change topics significantly. Although I should say that the distance between the eyes is called interpupillary distance. So sometimes called IPD. People who work in vision science, researchers in that area just call it PD, pupillary distance. So this will come up again. So the canonical view transform. So to make things reasonably easy to draw for me, let me assume that the eye is up here looking straight down. So you have to reorient with using your imagination. And so there's a straight down, and then we're going to be rendering ultimately onto a display that is rectangular. So because of that, there's going to be a rectangular boundary in terms of the field of view of the eye. For the human eye, it's not rectangular, right? We are engineering people. We engineer rectangles more easily than circles and other kinds of curves and things. But so there's a rectangular part to this that's going to begin here and continue through the whole pipeline. But if you ultimately have, let's say, a virtual reality display that is circular or some other shape, then it will show up in here, right? So there's going to be rectangular boundaries coming up. So imagine the viewing limits for the eye. There will be some let's say down here I want to render or draw a far plane, I will call it. So this will be called the far plane. And I want this line to come right down to and hit the center here. And then there will be a near plane. Put it up here. Well, I better, before drawing the near plane, let me connect the lines here. So I want to have the limits of how far I can see. Please forgive me if my lines get a little curvy. Let's see here. Or if they don't quite match, but they should be okay here. And let's see. So if I take a horizontal cross section, I should get a rectangle. That's what you're supposed to be looking at through this strange perspective drawing here. And then the furthest away plane where I'm going to consider is called the far plane. So any objects beyond that I will just consider to be out of bounds. They're not visible to the eye. So beyond the limits of this camera or eye, whatever it might be. There's also going to be a near plane, and anything closer than that is also going to be considered not within the limits. So I will put it up here. Let's see if I can get this one right. So I have another plane here. Again, this center line should be poking right through the center of it. Hit there, hit there, through the center. That should be in the center. We'll call this the near plane. Right, near plane. And then this part that we've gotten here, let's see. Let me shade this shape here that I get. Oh, I won't, let me see, I don't know what to do about the occlusion here. Let me just hit the outer boundaries here. So I will shade this, I will shade this, this, and this. I think I got all the outer lines there. So I did not mean to color this part. Let's just leave that here. So you should be see a shape there out of the pink lines that corresponds to a frustum. Let me try to draw this in another orientation now, this picture, where I have my eye coordinates. The eye frame. Z going away from the eye, Y going up, X coming out. Then I should have some kind of picture like this. Let's see here. Am I really going to get this right without making a mistake? Probably not. And let's see. Some hidden lines back there as well. Your brain will play some tricks on you because I haven't drawn the hidden lines correctly. I suppose I can use dashed lines for the hidden ones. We can go back and do that. Let's see. So this is the frustum. In particular, it's called the viewing frustum. That's what I was trying to show here in pink. Viewing. Is that clear? All right, so that's the geometric piece. I've decided on the near plane, far plane, and I want to figure out now for all of the points of our model in the world that appear inside the viewing frustum, I need to figure out where they go inside of this canonical viewing cube. This canonical cube that, remember, had coordinates plus or minus 1. So in order to do that, I want to set up a perspective projection model, which is going to take the frustum. It's going to look at points inside of here and consider the line that goes from each one of these points to the pupil. Right? So it's going to extend out like that. And you can imagine that the image that I'm trying to draw shows up in the near plane here, if you like. So in the near plane, you can imagine there's going to be a picture that shows up, and it's going to be where for every point that's inside here, inside the frustum, every point that's inside, it's connected by a line to the pupil, and at some point it strikes the near plane, and that's how I get my image. So if things are very large and close to the near plane, they're going to show up as very large in the image. But if they're the same size and then you move it further and further back to the back end of the viewing frustum, they're going to look tiny here because all these lines are going to come together and everything shrinks down to a point, right? So every point inside the viewing frustum, think of that as having an associated line. Moving from point space to line space is the basis of something called projective geometry. Turns out the homogeneous transforms that we did are also related to that, but I won't go into all those fascinating connections here. So because we're dealing with perspective projection and interpreting points as lines, I want to make a very simple picture. I want to drop the dimensions down and keep it very simple, explain the algebra, and then we'll handle the complicated case. So let's try to make a very simple side view of this picture here. So it'll be a two-dimensional version. So here is the focal point, or if you like, I've been saying the pupil location. Draw a horizontal line here, and a line off at some angle. And now I want to consider a point up here, P. This point is just any point that was in the world, right, after we applied the Fourier transformations to get into the world. And we then applied the I transform as well. So it's, I guess it's not quite in world coordinates, it's now in I coordinates. Excuse me, even though there's been no geometric distortion yet. And so if that's the case, based on this coordinate frame that we've set up, I have some distance ZP for this point. So the point, I guess I don't really have an x part here because of this projection, but you can imagine it looks like xp, yp, zp. And then this height here, let me move my p. Is yp, so I want the diagram to look like this. And so this is, again, this point is somewhere inside the frustum. And then I'll take the near plane up here, and suppose it's at a particular location here, and it's at some distance d. I'll remove, let's see, now I'll draw it up here. Okay, so here I will have this focal plane, if you like. This is the place where I'm going to be apparently drawing the image. It could be the near plane, it could be somewhere closer. I can move it all the way down and have it very, very close to the focal point. It's just going to shrink everything, but everything's going to be in the right place, right? So everything that I do, all the information is going to be in the right place. It just might need to be scaled differently. So I don't really care where I pick along here too much. It's just going to affect the scaling. And I can always redo the scaling. It's like converting from millimeters to meters or something. It's no big deal, right? It's very simple. So the scaling isn't going to matter too much, but let's just pick this particular plane here. All right, so I pick this plane. And now I would like to know what is going to be this height right here. So this amount h, let's call it, for height. And so one thing to notice, by the way, I've set everything up here, is that we have similar looking triangles. We have this smaller triangle here, and we have the larger triangle out here, right? So it's like a small triangle contained inside of a larger triangle, but they both have the same angle here, correct? Right? So I want to look at, these are both right triangles, and I want to compare these lengths h and y. I want to figure out what h is, and I want to look at that in terms of, or express that in terms of d, z, and y. Y and z are already given, and d is also going to be given because I've picked some place to make a kind of fictitious image, if you like. I just need to figure out what h is going to be so that it ends up in the right place. Well, one thing that's very important to projective geometry, or these perspective transforms, is that ratios are preserved of certain kinds. So I expect this ratio to be preserved. H over d is equal to yp over zp, right? Because this triangle on the left is just a small scaled version of the bigger triangle, correct? Right, so they're only off by scale. So these ratios of h over d and yp over z should be identical. So if that's the case, then this perspective transform applied to yp should be h equals, just solving this equation, let's say d over zp yp. I've organized it so that it looks like there's this extra term here, right? That's applying some kind of scaling to yp. It seems to be shrinking it by some appropriate amount due to these ratios, right? So that's all that's going on here. I just want to do the same trick now, but with more dimensions. And I want to make it work inside of my homogeneous transform matrices as well. So I want to increase the dimension and make it work in homogeneous transform matrices. Yes?
So what would be the angle? So the moving angle that we have for the
This angle here, this is the angle you're asking about. Yeah, this corresponds to, I guess viewing angle would be appropriate. So if this point P were in the center of the screen, if you want it to be exactly where you're looking, then the angle would become 0. And the angle could grow all the way up to some amount that corresponds to the boundary of the viewing frustum. I suppose when I look off on a corner here, I have the highest possible angle value. This doesn't have enough dimensions for that, so maybe I'm only looking at the top or bottom, which it also could correspond to the corner. So you could, so in 3D, you maximize that angle by going off to the corners. That's as far as you can look. If you had a spherically or a circularly symmetric image, then it would be the same angle all the way around would be your maximum limit. But as I said, we use rectangles in engineering, so it gets a little more confusing in higher dimensions. So yeah, good question. Okay. So let's see. So let's suppose I take this transform and I just kind of make it work by abusing our homogeneous transform matrices. And I say abusing because I think there's a culture of getting the homogeneous transform matrices to do a lot of work for you, even if they might not mathematically always look like they're doing the right thing they're doing the right thing mathematically, but they might not be the most intuitive or natural from a mathematical perspective. And part of the reason for that is that people in graphics are often reusing computational blocks and units They reconfigure them or reappropriate them, let's say, for another purpose. And so that's partly what's going to go on here, and I just want to show that again with less dimensions. So if I want to do this homogeneous transform, let's suppose I just want to start with yp and zp as 2 points. I'm ignoring x here because I've just eliminated it, let's say, 1 dimension lower, and then I'll add x in and add everything in a bit. So if I want to perform this transformation and I want to do it in a homogeneous way, I would take this point starting off as ignoring the x coordinate. I just have, let me see, if I'm just ignoring the x coordinate, I will just have yp zp. Normally when we do something in a lower dimension we drop the z, right? But no, I'm just doing it 1 dimension lower, dropping the x. So then I write it as a 3-dimensional vector because I'm doing homogeneous transformation matrices and I'm adding an extra dimension to it. So the 2D case becomes 3D. And then I want to calculate exactly this expression here by the following matrix. Oh, I guess I have room here. Okay, let's see. So I'll go D 0 0 0 1 0 Yeah, I'm suspicious. There may be a mistake. Let's see. Y P Z P 1 What do I get when I multiply this out? Let me see here. So I get DYP P. I get ZP. What do I get for the bottom? What's that? Oh, sorry, I don't even get anything more here, right? Is that right? Still not right. What am I doing wrong here? So let's see, that goes 2 by 1, 3, 3, 2, 1. You sure this is not okay? This is correct matrix multiplication at least. What kind of abuse we're doing to homogeneous transforms we haven't established yet, right? But at least I think the algebra is okay here. I mistakenly put a 1 here, don't need that. That cannot be right. So we have this, and I want to declare that this is y and h prime, and then I will define h equals y, sorry, up here is y prime, it's y prime and h prime. I will define h is equal to y prime over h prime, which when I multiply everything out becomes dyp divided by zp, which I think is this expression here. So what the heck have I done, right? So I'm going to use this extra h coordinate. This is the extra part of extension here for homogeneous transform, where I'm going to use the extra rho to calculate this h component, and then I'm going to use that as a kind of normalizer. I'm going to divide it out in my interpretation of the result. So I think that's kind of an abuse of the homogeneous matrices, but this is what's commonly done in graphics. So I'm just including it here so that you can get all the transformations you want, including the perspective transformation. It's not a linear transformation, is it? Right? If you look at z and y as variables, is this a linear transformation? No, right? There's a z in the denominator. So what they're doing is they're using the linear algebra structure here to perform the computations and then interpreting the result as, oh, I just divide by the last number when I'm done. So they still use the algebra here and then just divide by the h prime. Is that okay? That feels like a hack to me, some kind of hack. It works. I don't like it because you're using linear algebra, abusing it to do something nonlinear, and it causes a lot of confusion, I think. But this is done because, again, in the graphics pipeline, it's very convenient for them to just keep performing homogeneous transforms over and over again, and they can work to optimize the code that does that very efficiently, implement it in circuits, and then just continue onward and not worry about the problems of that. So, so that's why it's done in this way. Is that okay? So that's getting rid of some dimensions. I'm now going to do the 4x4 version. Here I did the looks like 2x3 version, right? So I want to now just expand this out and do the same kind of trick and give you the full matrix, and then we'll be done with this part. And I'm going to change notations just a little bit because I'm going to have a lot of variables coming in, and I want to have it be so that, let's see, we have, that's the z-axis, and we have this frustum, and I want to make this be called n for the near plane and this be called f for the far plane. And so now I will give T P, I will call it P for perspective. It's performing the perspective transform for us. It's going to finally be a 4x4 matrix. I'm going to put n here. N is now the replacement for D. Right, so I'm putting n here. I will have 0, 0, 0. I'm going to do the same thing now for the second coordinate. I'm doing it for the x coordinate here. I guess it was just y here. So I'm going to use the next coordinate, the second coordinate. I'm going to put it here 0, n, 0, 0. And this trick of 0, 1, 0, in order to get this appropriate denominator term, this will cause z to carry over. I'm going to put that here 0, 0, 0, 1. Oops. Wait, that one. Oh, sorry. No, 0, 0, 1, 0. Sorry. 0, 0, 1, 0. I'm afraid of the third row here. I'm not going to talk about it yet. So, so that gives us, without specifying the third row, you should be able to see that that's just a higher dimensional extension of this trick, right? So when I go and multiply all this out, I'm going to have the same thing happening now for the x and y coordinates. And the x and y coordinates are the main thing that I care about because you're trying to figure out what's going to go on the screen or the display, and that's a two-dimensional thing, and so you're going to figure out the horizontal and vertical components. But the graphics engine, the rendering part, is also going to have to figure out the depths and use that information, not figure out necessarily, but use the depth information to figure out what should be rendered on top of what. Like, is one object occluding another? It needs to know that. It needs to know this kind of information. So, so in order to keep that information and preserve it in some way, we have to put something else in this matrix. And so here's what's actually done. 0, 0, they put n plus f here and minus fn here. So think of that as the strange row where something unusual is going on. And so if I multiply everything out here and I try to figure out what the result is, suppose I apply TP. So I do, let's see, I try to figure this out. I do TP applied to x, y, z, 1. And if I apply this, what do I get? I get, you know, if we go ahead and do this multiplication, I get x prime equals, that's transformed x equals nx. I get y prime equals, well, I'm not sure if I'm comfortable with what I'm doing here exactly. Let me, I guess I need to put some brackets around these to make it look a little bit nicer. Just put one big equals for that. Y prime equals ny. And z prime equals something complicated, and h prime, the last one here, it's going to be the same h prime that I have on this for the lower dimension, right? So h prime equals, what's that one going to be? Z. Right? And now the z prime ends up being a little more complicated, so I need to widen my bracket here, and it's going to be z n plus f minus fn. So because of this matrix trick that's being used in order to perform perspective transforms, the z coordinate gets, let's say, somewhat mangled by the algebra. However, if you put exactly these terms in, then the z coordinates will at least be correct for points that are either on the near plane or the far plane. So that's just some algebra. If you work out the algebra, if you plug in z equals n or z equals f, and then you evaluate the expressions where you take you evaluate this expression, so you divide back out again, then you will see that it will preserve the z value in those two planes. And for the rest of the values in between, they will be incorrect, but the ordering will be correct. So when something's in front of something else, that will be correct, but there will be a distortion. It turns out that distortion does not interfere with the graphics pipeline, so people in graphics are just fine with that, because you'll still be able to judge what's in front of what else. But you know, do I like it personally? Not too much, because it makes the mathematics not clean. It makes me unhappy, and it comes from the abuse of a linear transform to do something that's nonlinear, right? So that causes for me a lot of confusion and headache, but it makes the engineering part more optimized, because you reuse these computations in hardware circuitry, right? So that's part of the motivation for that. All right, so is this okay? So we have that. Now one more thing we have to do after we perform this transformation. What we've done is converted the viewing frustum into a rectangular box, but we have not made the rectangular box have exactly coordinates plus or minus 1, and we have not centered it at the origin. So we have to do a scaling and transform to the box that we've made. So that's not very difficult. It's a very simple scale and transform operation, as I said. Nothing weird going on, but we have to put this into the pipeline of transformations, into the chain of transformations. So if this is what the rectangle looks like by the time we're done, the viewing frustum gets converted into a rectangular box. Then I want to say that this corner here will have coordinates L, B, N. N is still for the near plane. L is for left, and B is for bottom. And then over here, let's see, I better make sure I have opposite corners here. Should be up here. I have a mistake on my notes, but I think I'm going to get it right here. R, T, F. So far plane, top, and right side of the box, right? So I'm just going to use all these letters so that I can put them into the matrix very easily. So I have one more transform called T. I'll call it ST for scale and transform. This in Shirley's book is called T orth, if you're looking it up there. But instead of emphasizing orthogonality, I'm going to emphasize it's just a scale and a transform. So scale transform. So if I want the coordinates to be plus or minus 1, that means the cube is going to have length 2. So my scale is going to be, for the x coordinate, 2 divided by r minus L. And then I'm not interfering with the rest because I'm doing no shearing. And then my scale for the y coordinate is going to be 2 over t minus b. And then the scale for the z part is going to be 2 over n minus f. And then I'm not going to do anything on the bottom, of course, not doing any strange trickery of abusing homogeneous transforms. And now up here, in addition to scaling, I have to center this box as well. So that's what the translation part is going to be. So it's just going to be minus r plus L over r minus L. And all these look similar. I guess the minus is out in front here. So minus t plus b over t minus b. And minus n plus f over n minus f. Whew, so now we have that. And so now I can finally put together for you the canonical view transform, which is T can, which is equal to T ST TP. Because the perspective transform is performed first, and then the scaling and translation transform is performed, so that you end up with a pretty box with coordinates plus or minus 1 with respect to the x, y, and z axes respectively. Okay. So how's that? Does that seem fine? It's nicely separated, I think. So the interesting perspective part is in one chunk. This weird kind of math hacks that I'm not completely comfortable with, but I see that they work, are performed to generate this matrix TP, and then we have to do the scaling and translation part in order to make a nice box with standardized coordinates. It wasn't a necessary step, but it makes it convenient for a lot of algorithms that run in computer graphics to keep all the coordinates in a nice normalized form. Again, some people might want to go from 0 to 1 instead of -1 to 1 for all these coordinates, in which case that changes this transform a little bit, right? The scale will not have 2's here in the numerators, and these translations will be appropriately changed. So, not too difficult to figure out. Questions about that?